Okay, determining a chemical formula from experimental data. So this is how you find the empirical formula for a compound. And we can do this by analyzing the masses of elements that form if we take a compound and decompose it into its elements, or the masses of elements that react to form a compound. So we can use that to calculate the empirical formula, or we can use the percent composition. It's important to remember that the empirical formula is a ratio of numbers of atoms or ions, and it's not their masses. So we have to get to moles. So these are the basic steps. Write down the masses of each element present. Sometimes they'll give you the masses, sometimes they'll give you a percentage. If you're given a percentage, then you can just say, well, let's pretend I had 100 grams, and then the mass is the same as a percentage. That makes it easier, because the percent composition doesn't change depending on how much stuff you have. Then we're going to convert the masses to moles using the molar mass of the element. And then we need to find the smallest whole number ratio. So we're going to divide the moles of each element by the smallest one. We're going to do that so that our smallest ratio is 1 and everything else is 1 or greater. We don't want a ratio of 0.5 or something. If your result is within 0.2 of a whole number, you can round it to the whole number. What do I mean by that? Well, if I get 1.87, that is within 0.2 of 2.00, right? Because that's what, 0.13 apart? If I have 1.74, can I round that to 2? No, I can't. So we'll see what we have to do for that. What if my subscripts are not whole numbers? Then we're going to multiply all the subscripts by the same small whole number so that we can get close enough to round to small whole numbers. So if the fraction on your ratio is one of these, this tells you what you should multiply to get a whole number. Or you can also do the trial and error method. Try multiplying by 2. That didn't work? Try 3. Try 4. You almost never have to go past that. Okay, I'm going to skip that other problem and I'm going to do this one. So, because with the percentages, there's a little more to explain. So ibuprofen has the following mass percent composition. 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen. What is the empirical formula of ibuprofen? So in this problem, I'm not given masses, I'm given a percentage. So I'm just going to choose to have 100 grams, and then my percent is the mass. So I've got 75.69 grams of carbon. I need to convert that to moles of carbon. So periodic table says 12.01. So I'm going to get 6.302 and some other digits. For the hydrogen, it's 8.80 grams of hydrogen, and I'm going to convert that to moles. .730 and 15.51 grams of oxygen. can I round? Oh wait, I don't want to talk about rounding yet. The next step is dividing. So I'm going to look at these number of moles. This is moles of carbon and moles of hydrogen and moles of oxygen. I'm looking for mole ratios. So I'm going to pick the smallest number and divide everything by the smallest number. So one of them is always going to end up exactly 1. So 8.730 divided by 0.9694 equals.
Where did you get the 0.964 again?
I got that because it's the smallest number of moles.
Oh, okay.
Yeah. Thank you for asking.
Thank you.
Okay. So can I round 6.5 to 7? No, I can't. So what that means is I'm going to have to multiply all of these by some number to get a whole number. I think most of us recognize that 0.5 is half, right? This is 6.5 moles. So if I multiply by 2, I'm going to get a whole number. So I'm going to multiply this by 2 times 2 equals 13.00. Well, let me use the rounded number. 0.02. And if I multiply one of them by a number, I have to do it the same, because otherwise they're not going to be the correct ratios anymore, right? I'm going to mess them up. So this is 18.012. This is going to be 2. This is close enough to round to 13. It's extremely close. And this can round to 18, and then I've got 2. So these are the subscripts then in the empirical formula. Carbon has 13, hydrogen has 18, and oxygen has 2. Their ratios, there's 13 carbon atoms for every 18 hydrogen atoms for every 2 oxygen atoms. We have to have whole numbers here because you can't have a molecule with 6.5 carbons in it. So that is the empirical formula. Any questions? How do we get the molecular formula? We need another piece of information. The molecular formula is going to be some multiple of the empirical formula. In order to find that molecular formula, you're going to need the empirical formula and the molar mass. In a problem, they're going to give you the molar mass. So what you're going to do there, because we know that the molecular formula is the empirical formula times some integer. We're going to take the molar mass, that's the mass of the molecular formula, and we're going to divide it by the formula mass, the empirical formula molar mass. And this should give us very close to a whole number, and that tells us we have to multiply all the subscripts by that number. Okay, a compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? So we're looking for this multiple, right? And so, or multiplier. We're going to take the molar mass and divide by the empirical formula molar mass. Well, the molar mass is 78 13.11 grams per mole. We have to calculate the empirical formula mass. It's carbon, 12.01, plus hydrogen, 1.008, 13.018. So our empirical formula is 13.018 grams per mole of the empirical formula. 78.11 divided by 13.018 equals 6.00015. That's 6. So that tells me that the molecular formula has 6 of these units in it. So you could think of it this way. You've got that empirical formula times 6. That's not how we're going to show the molecular formula, but that's just kind of how we're thinking about it. We're going to take the subscript on the carbon, which is 1, and multiply by 6. And the subscript on the hydrogen, which is also 1, and multiply by 6. And there is the molecular formula. If you calculate the molar mass of the molecular formula, you're going to get 78.11, or really close. Combustion analysis is a technique for finding the empirical formulas of compounds that will burn. And so it can be used for organic compounds that contain carbon, hydrogen, and oxygen. When these compounds burn, all the carbon that was in the compound becomes CO2, all the hydrogen becomes H2O, and then to find the mass of oxygen, we take the mass of the original compound, subtract the mass of carbon and hydrogen. This is a diagram of combustion analysis. So you put your sample in here, you're going to weigh it and put it in here. It's a furnace, and oxygen flows in here. As this burns, the carbon becomes carbon dioxide, the hydrogen becomes water, and any oxygen just goes along. So we're going to flow oxygen through here, and those gases that are being given off are going to be forced through these tubes. We used to call those U-tubes, but it's something else now. Through this tube, and this has a substance in it that absorbs the water. And then it has to go through another tube, and this has a substance in it that's going to absorb the CO2. So you weigh this tube before and after, and the difference is the amount of water given off. You weigh this before and after, the amount of CO2 given off.
Would we need to know how for the acids we had aqueous, because CO2 is a gas needed, but G for that, not necessarily?
Not necessarily, no. So I'm not going to do that example. We have more important things to spend our time on. Okay. There will probably be a combustion analysis problem on the exam as kind of a challenge, but it would be one like this where it's only carbon and hydrogen, and there's carbon, hydrogen, and oxygen. It just gets even messier because then you have to find the carbon and hydrogen and subtract them to find the oxygen, and right? Okay, so end of that.